Pretty good. Thanks. Yourself?
Yeah, so Jack, I saw your email. So I think it's better
Yeah.
if we talk in here, and then it's much easier instead of like just replying emails.
Yeah, I think so. Yeah, I
Yeah, sure.
agree.
Yeah, so let me see how what we can start. Do you want me to share your email with questions, or we just talk about
I
it?
guess maybe I think it was activity one.
Mm-hmm. Or
Um,
or if you want, you
on
can share your screen. Yeah, but
yeah,
I mean,
okay,
I'm recording. If it's something you don't want to show, then that's totally fine.
okay, yeah, yeah, yeah. I can share my screen.
Yep.
Um, Second. Okay. Okay.
So it's about triangulation, right?
Yeah, 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 yeah. Triangulation.
Yeah, sure.
3D reconstruction.
Yeah, sure. Yeah. So probably I can start with something. I saw your email. I read your emails. I
Yeah.
think first of all, the focal length and principal point
Mm,
and image points, they are all in pixels. They don't have an actual meter. So it's not in meter, it's not in millimeter. So focal length, principal point, and image points, they are in pixels. So you don't have to
okay.
convert it. You don't have to convert it. Then if we come back to the equation just at the end of the previous slide, is z equal to b times f divided by d, right?
Yeah.
Then you can
So it's
see
meters.
b, yeah, so b is in meter, right? And
Mm,
focal length is in pixels, and d is in pixels. Then which means z is in meter. That makes sense, right?
okay. Yeah, yeah, yeah. That makes sense.
Yeah, sure. Then
Cool.
come back to your question. So you don't have to convert focal length to any of the metric. But
Yeah.
the thing is when you use the image points, left and right,
Yeah.
first of all, you need to move the origin into the principal point. That's the first step.
Yes.
Yeah, so if you look at the figure, so C is the camera center, right? The red point is the camera center, right?
Yeah.
And you can see that the XL is from the principal point to the pixel, not from the top left of the pixel. So normally if someone's giving you a UV value of pixels, then
Mm,
that means the origin is top left already. So we make it a principal point offset. But when we calculate the triangulation, then we have to like move the origin back to the principal point, right? So that's
right.
the
So
first.
in this, yeah, I think I follow. So in this
Yeah,
question, we've got for the left camera, the
yeah.
I guess for both cameras, the principal point is in the X dimension 400. So
Mm-hmm.
does that mean so you've got the camera here.
Mm-hmm.
Does that mean the principal is this the principal point here?
No,
PL
principal
is
point
here.
is, yeah, it's there. That's right,
Is
it's there.
there? And
Which
so
means
if the
if this
val
is
if the
400, this 400, and the green point will be 300. But anyways, it's on the other way, right? So which means you have to
okay.
use 300 minus 400, something like this.
Okay. So if the position of the principal point in the coordinate system of the image of the image plane is this is a 400, does that mean the origin of the image coordinate frame is over here somewhere?
Yes,
And
that's
then
right.
it's
That's
like
right.
plus
That's right.
400.
Yeah, yeah.
Okay,
That's
I see.
so right. Yeah. So if you go back to the next slide.
Yeah.
Yeah. So the first thing you need to do is, let's say your image point left is 300, right? You need to make it
Mhm.
as like XL XR is equal to, sorry, XL YL is equal to 300 300 minus 400 300, which is the principal point.
Okay. Yeah.
Yeah,
So you
that's the
minus
first.
the principal point offset.
Yeah, and then you get XL and YL, and the same to XR and YR. So you need to use 200 300 minus 400 300.
Okay. Okay. Yeah,
Yeah.
that makes sense. Cool.
Yeah, and then you have your XL, YL, XR, YR. And then you put them, probably put XL in this case into the Z function in the previous slide. Then you have the yeah, and then apply the other one on the top left. Then you have X, right? And similar to Y, something like this. But in this case, yeah, in this case, the YL and YR, they are 0. Zero means the coordinate of Y is 0, right? If you put it in. So that's it.
Okay.
Yeah.
Okay.
So probably have a try.
No,
I think after I explain it to you, probably you have a better idea on that. Have a try and to see if you can get the correct answer. And then if you still have some questions, you can come back to me and I can explain it to you again.
Okay. I think I had a go at the solution. I might be able to get it on the screen here. Yeah. So here, I think this is the one we're talking about now. The parameters, the problem parameters are a bit different. They're listed here. So I think the first thing I did was as you said, it was account for the principal point offset. That is that's just the
the UL minus EX, right? Yep, that's right.
That's and then so from there, then you would just apply those formulas.
Yeah. So which one is your XR? The only XL. Oh, XR is there. All right. So XR, you still need to use like UR minus PX.
Oh yeah, I did that. I just didn't bother with the working out because it was like the same working out as this, just for the right camera.
Yeah. And then you put that in to get Z. And then after you get Z, you get X. Then when you use X, you need to use the XL, not UL, right? So XL is minus 338. Yeah. So I think it's correct.
Okay.
Yeah, it's minus 0.4 something, right?
Yeah. Okay.
I think
it's
correct. Yeah.
So in the question then, when you're given like XL and YL, what exactly is that?
All right.
What does that correlate? I've got here, maybe I'm not sure if it's true, it's the point with respect to the image coordinate frame with the principal offset already accounted for.
All right, sure. So let me explain it one by one. I think it's when we introduce the cameras and how to use it, how to do the projection, and the other way around, how to do this triangulation if you have stereo, right? Then in this case, let's say what you're watching, what you're seeing is an image, right? Yeah. And then normally for an image, then the top left will be 0 0.
Top left. Okay.
Top left will be 0 0. So let's say if you have a pixel on the bottom right, so probably that is 840 by 480, something like this.
Yeah.
So that's the resolution, something like this. And then for a camera coordinate system, it's a little bit different. It's similar, but it's a bit different. So if you can see that picture you draw on the top right. So the camera system is kind of like the camera center is 0 0 0 0 0. It's 3D, right? And then pointing out, directly pointing out.
Yeah, principal axis.
That is Z. That is Z, right?
Yeah.
Z axis. And then if you can see there's an intersection between the Z axis and the image,
Yeah.
that is the principal point.
Okay.
All right. So
got
which
you.
means
Yeah.
in the camera system, the principal point is 0, 0 on the image, right? But it is not.
Yeah.
Because we normally make top left as 0, 0. So which means that's why when we do the projection, we have a principal point over. So which means if you have a UV value, so normally the UV value represents the image coordinate with respect to the origin on the top left.
Okay. Yeah, I get you. And when you
Okay,
actually get when you're actually looking at an image and you're trying to map that to the real world, you'll have the U and V, and you're just working backwards from there.
Yes. So that
Okay.
yeah, you are right. You are right. When we do the triangulation, let's say we're calculating the 3D point position, right?
Yeah.
Then
yeah.
it is in the left camera coordinate frame. The left camera coordinate frame means Z is pointing out, and 0 is on the principal. So this is what you get for for the 3D point. Yeah.
Okay. Okay. Yeah, that makes sense then.
Yeah, sure. Yeah, sure. Probably like have these answers and go back to review like what you have and also what you like what you get for the solutions, and probably have a better understanding on that. But anyway, if you have any questions, call me back. I'll be here for 2 hours.
Okay.
Cool. I'll be another 2 hours on one day. But anyway, so if you can't join those 2, then send me an email and then saying like can't join, then I probably like reply to you.
Okay. Yeah, no worries. I'll probably hang around and just observe anyway. But thanks for your
No worries.
help.
No worries. All right. See you. Jack, you don't have to stay here. So I'm recording and I will upload it today for today's consultation if you don't have further questions.
Okay.
Yeah.
Thanks.
No worries. See you. Hi, Van. How's everything?
Teacher, where do you upload the video?
I will upload the video to Canvas, and then I'll mention that. I'll send an announcement and mention that. Where is it?
Is the video today or the next day?
Yeah, I'll upload it today. Yeah, so I'll upload it right after I got the record from the cloud, and then I will upload it. So probably I will do it today, probably a little bit later. Yeah.
Yes, thank you, teacher.
Yeah, no worries. So if you don't have questions, just want to listen, you don't have to stay here, because I'm recording. Yeah. All right, cool. So Sonu, sorry.
Hi, Lian. I have a question about the question is in the lecture 9.
Lecture 9. So do you mind if you share the your screen with the lecture notes?
Okay, let me share my screen. Can you see my screen?
It's coming. Yeah, I can see it.
Oh, this is the question.
Yeah.
A second. So I try to, sorry. Just a second. I try to solve this question.
Yep.
So, but I'm getting a different answer from the answer given here.
All right. So can I see what you did?
So what I did is, so I took the K matrix. So that was a matrix with the focal length, and for px and py we do have to take the 0, 0 for this one. I think this one the
principal point is 400 principal point.
So it will be 400.
Yeah, so if the image resolution is 800 by 800, and if the principal point, normally principal point is around the middle, but sometimes it's different. Right here, we just suppose in the middle, so in the center. So center means 400.
Okay, and then we have to multiply it with the rotation matrix and the translation matrix, and then multiplied by the 3D point, 25, 50, 80.
Yes, I think I have a code uploaded to the
Yeah, I have seen that code, but in that code, I think we don't have the rotation and the translation
we don't
matrix.
have it, right? So yeah, okay. So can you go to some previous slides showing the general projection? Then I can explain it to you, like, and corresponding to this question. No, probably can you make it smaller? Yeah.
Just a second, please. Second. This one? Maybe.
Wait, where is it? Where is it?
That one is in the
Probably next,
camera
probably
frame.
next slides.
Yeah.
22. There 22.
Yep.
Okay, here we go. Here we go. All right. So can you this is 22, probably. Can you go to the next slide? Next one. Here we go. Here we go. This is one. This is one. All right. So if you look at the projection function on the bottom left, the small x is equal to k times r times
R.
3/4 and times x, right? So k is the calibration matrix, you know that, right? So you can find it. Yeah, and r is the rotation matrix. Yeah, so if this a set identity matrix, which is the 3x3 identity matrix, right? So it's nothing, you can cancel it. And C, the C here, the C bar here is the T translation. But do remember there's a minus here. There's a minus in front. So the total, so I mean the matrix there is the 3/4. So with the first 3x3 as identity matrix, and with the last column minus translation, minus T or minus C.
Okay.
Yeah, and then the X is X, Y, Z, and 1. It's
that's 3D point in the world coordinate frame.
Yes, in the, yeah, that's right. That's right. So probably if you apply for that, you can get the answer. Probably have a try.
Yeah, and then we just multiply all of these matrices and we get 3 point, and we divide the first point by the third and the second point by the third point.
Yeah, and then you get UV. Yes, that's right. Yeah, that's converting from a flow. Yeah, sorry, when?
Excuse me, teacher, with the I, with the matrix I.
Matrix I is the identity matrix, 3x3 identity matrix. Identity matrix means if you have suppose this is 3x3, right? So you have a 3x3 matrix with the elements on the diagonal, they are all 1, and off diagonals, they are 0. Something like this.
So
and
Sorry, when?
So
sorry, so no, probably you can say,
yeah. So this translational matrix has a minus sign in front, so we have to consider that minus sign as well.
The C one, not the I, not the identity matrix, the C.
Yeah,
right?
The C one. Yeah, so we have
let's say C is T. T is XYZ. That's a translation or camera center location, right?
Yeah.
And then you just minus X, minus Y, and minus Z. That's it.
So the whole matrix will be like 1, 0, 0, and the X coordinate of the translation with a minus sign, then 0, 1, 0, 1, 0, and then Y coordinate of the translation matrix with a negative sign, and
Yep.
then 0, 0, 1, and the Z coordinate with a minus sign, and then 0, 0, and 1. This is the whole. This will be the whole.
No, it's 3 by 4, so you don't have the very last row. Sorry, very last column. Sorry, very last row. Yes, it's 3. It's 3 by 4. The whole
So
matrix.
okay.
Yeah.
And
Yeah. The first three rows are perfect. Yeah, you are right.
Yeah, and the rotation matrix, it will be just 3 by 3 identity matrix for this question.
Yes, that's right.
Yep, and the X will be, so if it's a 3 by 4 matrix, so it will be a 4 by 1 matrix. Yeah,
That's right. That's right.
X, Y, Z, and then a 1.
Yes, that's right. That's right. That's
Okay.
perfect. Yeah, have a try. And yeah, probably. I think.
I didn't took that minus sign because I have seen somewhere. So they have, they didn't took the negative sign. So they just they make the rotation and the translation matrix as one matrix. They multiplied it with by K and then with the X. So I think
Yeah.
that's the problem.
So I think different sign has different meaning. I mean, I guess that probably the problem. That's why I come back to you and show you there's a menace, right? But let me explain to you physically about why there's a menace, right? So suppose you have your camera, right? You know the camera pose with a rotation and a camera position, or we call it translation, right? Then the when you project the 3D point, which is in the global coordinate frame, then we first need to transform it into the camera coordinate frame and then project it, right? And this equation is derived from there. Then think about when you transform a point into the camera coordinate frame, then you need to move the origin to the camera center, which means you need to minus the position of the camera center, right? That is why there's a minus.
Oh, okay. Okay.
Yeah.
Thank you.
Yeah, probably have a try.
Yeah.
And see how it goes. Yep.
Yeah. Okay. Thank you.
No worries. No worries. Thanks, Sonu. Any questions from you?
Yeah, can I just ask you a question about that last one?
Oh, yeah, sure. Yeah, sure.
So if you wanted to apply a rotation to that, would you just multiply the identity matrix that's used for the R value? Would you just multiply that by, like, if you were doing it in MATLAB, would you just do it like T rot X and then a radians value?
Sorry, can you repeat your question? So if we do it in MATLAB, we just apply it as just use that equation, and supposing you have R and you have T, and just put it into the correct matrix and multiply them together, and that's fine. Yep.
Yeah, okay, because the R matrix, it'll be, because it's meant to represent the rotation.
Yeah, that's the rotation. Yes, you are right. That's the rotation, and it will be always 3 by 3.
Okay, and it'll be, you need to generate that because you won't be able to sort of do it manually, right?
Hey, that's a good point. That's why I think I put that question into an zero rotation, because because there are different ways to present a 3D rotation. I explained it a bit more, and then coming back to your question, right? So a 3D rotation, normally we present it as a rotation matrix, which is a 3 by 3 orthogonal matrix, something like this. And then its inverse is equal to its transpose, something like this. And then there are different ways to parameterize it. Probably you heard of it. One is cotangent, and the other is Euler angle, and the other is axis angle, something like this. So it is, yeah, I totally agree with you. So presenting a 3D rotation matrix is pretty hard. And there are different ways to transform it, to define the parameters and transform it. So that's why in that question, I just say that the rotation is 0. So which means rotation matrix is intensity matrix. So which means there's no rotation. So if there is a question telling that the rotation is something, especially in this subject, I'll let you know what is the rotation matrix exactly.
Okay.
Because I mean it's pretty hard telling you that the Euler angles are like
Yeah.
3 angles and ask you to convert it, then it's a pain, right? But probably in your future work, probably if you use the rotation matrix, then I'm just telling you normally there are 3 ways to present it, right? So one is Euler angle, the other is cotangent, and the third one is axis angle. And in MATLAB, there are certain functions you can use to convert the parameters into rotation matrix and the other way around.
Sorry,
But
sir.
In this subject, we will not using that. Yeah.
Okay. Okay. Thank you.
Sir.
No worries. Yeah. Hi, Wen.
Can I ask you?
Yeah. Sorry. Just wait a second. So, Sachin, so do you have further questions? Probably I can answer your questions for all, and then we can come back to Wen.
Oh yeah, I was going to ask about the visual servoing as well.
Yeah.
For the calibration, I was wondering if we can get a question where there's like 2 focal lengths, like we can get for the other types of camera questions. So like there's one for the X and for the Y. Because in the tutorial example, they don't solve one that has that. It's just one that has 1 focal length. And yeah, I was just wondering because it's come up in other camera stuff. So I was wondering how to solve that.
Yeah. That's a good question. I think we mentioned that in the reflection of quiz 1. So why we have like fx and fy, so 2 different numbers for a same focal length. That is because the pixel is not perfectly square.
Yes. Yeah.
The focal length is in pixels, right? Then in the x and y directions, we calculate it into pixels. But if the pixel is not perfectly square, they may be a little bit different, right? But they can't be so different. So if in the calibration you have a very different focal length fx and fy, so which means probably the calibration is not very accurate, right? But anyway, coming back. So in the projection, I think you know how to deal with it, right? So when you calculate x, you use fx. When you calculate y, you use fy, right? But in the Hanai calibration, I didn't mention it so like complicated because I want all of you to understand the process about doing visual serving instead of like getting very details about how to use fx, how to use fy. But I mean, when you apply it, it is similar. We are not going to like making questions about fx and fy. So if we have video serving one, right? So from our point of view, so we want you to know how to do video serving instead of getting very detailed. So let's say if you really have a question with video serving and have a different fx and fy, probably just average it and apply it. It doesn't, in the engineering point of view, it doesn't affect too much. It will be affect a little bit on the accuracy if you really use it in this way in the real case, but it doesn't affect too much. Probably you can do that, and we will not get any mark from that. Don't worry. Yeah, but anyway, so if you want to make it in very detailed and apply it like 100% accurate, then in the equation, anything related to x or u, you use fx. Any equation related to y or v, you use fy, and that's it. But anyway, this is not the purpose we are aiming for. We're aiming for letting you to know the process of video serving. That is more important.
Okay, I was just checking that we didn't like have to know that because it wasn't in the tutorial.
Yeah, sure. You don't have to. So if there's a question telling you that there's an fx and fy, then you are doing video serving, right? Then probably just average it. That's fine.
Okay, so like find the absolute value of them or something, and then use that if we got a question.
Yep.
Okay.
That is the question you're asking, right?
Yeah, because yeah, I don't know. I was just checking, but yeah, okay, thank you.
No worries. All right, cool. So sorry, your question?
I want to ask about visual serving. Is it like inside the program, inside the test?
Sorry, what's your question?
I mean, do we need to study into visual surveying?
Sorry, can you repeat your question? I didn't get your question.
I mean, so do we need to study the part from the visual surveying, like the chapter 10?
I can't say exactly what we have in the final exam, sorry, because it's only 30 points, probably like 2 to 3 questions with sub questions. I can't make it very detailed, right? But if there is a visual surveying question and probably it's asking about calculations, then yeah, I'm happy if you use the example code and modify it to help you for the calculation, but don't copy and paste code in it. I still want to see the important process of solving it with necessary equations there. And MATLAB or the demo code is just helping you to do the calculation. Did that answer your question? Sorry.
Yes, sir. So we just write the formula there, and the result is from MATLAB, right, sir?
Yeah, so it's kind of like if there's a calculation problem, let's say, and I can't say if there is or not, but if there is, so what you need to do is you need to write the process about the progress about solving that question with necessary equations, and everything related to calculation you can use MATLAB or you can use the example code to help you to do the calculation, but
So
don't copy paste codes.
yes, sir. So I just write the formula and the number. So I just have the number and the step. So we have the result, right, sir?
Yeah, if there's a calculation, you need to have the results definitely, and also I want to see the result of any like in the middle progress, right?
Yeah, thank you,
so
sir. Yes.
yeah, you can use MATLAB to help you do the calculation.
Can I ask you just like how many questions in total in the test?
Yeah, I did it about a month ago. I think it's 2 questions with sub questions. Yeah, but I mean it's only 30 points, and you have totally 2 hours and 40 minutes to finish it. So I believe time is enough.
Can I ask about the formula that's the student solve there? Is it K or I minus C mean times X? So all of them is the 3x3 matrix, sir. The same size.
Yeah, so do you mind if you can share your screen, then we can talk about that. So you're talking about the general case of the camera projection, right?
Yes,
I'm
yes,
guessing.
sir. Yes.
All right, so do you mind to share the screen and show the equation? Then we can talk about it together.
Yes, sir. Just 1 second.
Yeah, no worries. Take your time.
Oh, yes, sir. So I mean this camera projection. So is it all of them should be 3x3 matrix?
Yeah, it's a pen. Why is like that? Okay. Let me show you on that. So we are talking about the equation in the bottom left, right?
Yes.
Okay. So let's talk one by one, right? So the small x on the left hand side of the equation is
You
a
mean
3
this
by
one?
1. No, left, small x.
Yes, sir.
Yeah, that is 3 by 1.
Yes.
Yeah, 3 by 1 means a homogeneous point of 2D point. And then if you want to convert it into UV, so you use the first element divided by the third one, you get U, and you use the second element divided by the last one, then you get V. So that is only for small x. I'm only talking about small x at the moment.
Yes, sir. So
Is that
3 by 1, you mean Si and 1, right?
No. I'm not saying x, y, and 1. It's 3. It's 3 by 1. And when you want to convert, this is what I mean, why I'm talking about that. So when you want to convert this small x into UV, then you need to use the first element of the small x divided by the last element of the small x, then you get U. And you use the second element of x divided by the last element of small x, then you get V. Is that clear?
You mean this?
No. I'm talking about only small x in
Yes,
the
sir.
bottom left equation.
So K or you have UV.
No. I'm only talking about the small x.
Yes, sir.
All right,
So
I'm only talking about small x.
if the small x is 3 by 1, so what should be like SYZ or SY1? Because 2D.
This is I'm talking about. This is
Yes,
I'm
sir.
talking about. All right. So now I'm only talking about small x. Is that okay?
Yes,
Is that clear?
Yes.
Okay. So when you have a small x,
Yes.
it is x, y, z, x, y, t anyway. So there are three numbers, right? In it. It's 3 by 1.
Yes, sir.
All right. So when you want to get the UV values from the small x,
Yes.
then U is equal to the first element, the first number of x divided by the last number of small x. Is that clear for you?
Yes, sir.
And when if you want to get the V value, V is equal to the second number of small x divided by the third number of small x.
So you mean your last number of small x?
No, the second number of small x divided by the last number of small x.
Thank you, sir.
Is that clear?
Yeah, very clear. Thank you so much.
Okay, cool. Okay, so now we're clear that how to convert the small x into UV, right? How to convert a 3 by 1 vector into the image position UV, right? So that's clear. Can we say that?
Yes, thank you so much. Yeah.
Okay, cool. Then let's look at the right-hand side of that equation, right? Yeah. So K is the camera calibration matrix. And you can find K somewhere, I believe, in the previous slides. Are you clear about what is K?
So it's just like camera projection matrix.
No. Let's talk about K times R times the matrix times X.
Yes.
Let's talk about that, right?
Yes.
Okay. So do you know what is K?
So K is like camera intrinsic parameters.
Yeah. So do you know what exactly the K is?
No. Sorry, sir. I didn't know.
No, don't worry. This is something I want to confirm. So can you go to the slides upper or lower? So probably like in the previous slides.
Yeah.
If you go go up. If you go up. No, probably go down. I have a slide showing what is K.
Maybe another slide.
If you go down.
It's over. Sir.
This is a review. I don't think I only have 12 pages on that. That's warm up. Yes. Yep, go down. I think I have like video records. I explain it very clearly about what is what. No, I think you go too fast. Probably I can see from my side. I'll let you know. I do have a metric saying what is K. Let me see. Give me a second.
Yes, sir.
Sorry, just give me a second.
Yes, sir.
Yeah, my internet is very slow here. Can't be loaded. How can I do? Here we go. All right, so can you go to any page? What's that page? Page 26?
Yes.
Are we talking about the same? No,
Is
it's 30, it's 39 already. It's 30 already. So if you look at,
Oh, here, sir.
yeah, here we go. Did you see K? 26.
Here.
Here we go. Yes. Did you see what is K? That is K on the bottom.
Focal length and points X and Y.
Yeah, so P, X, P, Y, they are coordinates of principal point. Focal length, principal point X, principal point Y, and 1. That is K. Is that clear for you?
Yes.
Okay. Okay. Can you go back to the slides with your questions?
Yes, sir.
Yeah, there we go. So we know what is K, right? That's a 3x3 camera calibration matrix or camera intrinsic matrix, right? And R is a rotation matrix. A rotation matrix means if you have a camera and the camera is in the global coordinate frame, right? And
yes.
There is a pose of the camera telling like what's the camera pointing out, what's the rotation of the camera and what's the position of the camera, right? So rotation means the rotation of the camera, which part of the pose of the camera, right? So R is a 3x3 matrix. And again, you don't have to care too much about that. I will tell you what is it. So in the question before, then R is an identity matrix. Identity matrix means on the diagonal is 1, 1, 1, right?
Yes.
And all diagonals, they are 0.
Yes.
Is that clear?
Yes.
Okay, cool. So you know what is R, right?
Yeah, no.
Okay, okay. Then let's look at the other metrics. Right? I think the display, it was pretty bad, but it's something like the first 3 is a 3x4 matrix. It's a 3x4 matrix, and first 3x3
Yes.
is an identity matrix.
Yes. So
the last, sorry.
So it's identity matrix.
And then the first, it's a 3x4, right?
3x4. Okay.
3x4, and with the first 3x3 identity matrix.
Yes.
Okay, and the last column is minus C or minus T, which is the minus the camera center or translation.
Okay. You mean
I think Sonu gave explain everything very clearly on that matrix.
S-cam or what?
No, don't talk about that. Don't look at that. We are just looking at that equation. Okay.
Yes, sir.
Do you know what is that matrix, the 3 by 4?
No, what I mean, after
I
all,
can, I
right?
can share a board. I can share a board for you. I can
Yeah,
share a
thank
board
you.
for you. Let me see. How can I do? Whiteboard. Right. New whiteboard. All right. So can you see the whiteboard?
Yes, sir.
All right, cool. So my handwriting was pretty bad, but I mean, I'm trying to write it. Pen. All right. So now we are talking about the what I called, that is I and dot, sorry, minus C, right? We are talking about this matrix, right? And that is a 3 by, sorry, my handwriting was pretty bad. 3 by 4, right? That is equal to, I don't have a mouse, that's easy. 0. Sorry, this is 1. What can I do? Can I erase it? But anyway, this is 1. This is 0. This is 0. This is minus tx. This is 0. This is 1. This is 0. This is minus ty. And this is 0, 0, 1, minus tz. Is that clear?
Yeah, it's very clear, sir. Thank you so much.
Okay, cool. So that is the matrix, right? This is what Sonu mentioned, right? And the last question is, what's the capital X, right? The capital X is 4 by 1. That is, if you know the 3D position of the global point, right? So that is X, Y, Z, and 1. All right? Is that clear?
You mean the homogeneous vector, homogeneous coordinates vector?
Yes, yes. So if in the question I'm telling you that that's the global position of the 3D point is X, Y, Z. So in that
Can I ask you? Yes,
in
sir.
that equation, use X, Y, Z, and 1.
Is it X 4 by 1 is the homogeneous matrix?
Yes, it is. It is. It's a homogeneous point of the 3D point. And the small x is the homogeneous point of 2D point.
Thank you so much.
Okay, so then everything's clear. Then the small x is equal to the k times r. Sorry, I use this time. It may be clear. And times this 3 by 4. That is, that is I. Minus C times this capital X. Is that clear?
Yes, sir. So
all right. So you know everything, right? You know what is K, what is R, and what is this 3 by 4 matrix, and what is the capital X. Then you can get this small x.
yes.
Right?
Can I ask, the small x is SY and 1 or SY?
Oh God, you still don't get it. Let me explain it to you. All right. So this small x is 3 by 1. Okay.
Yes.
That is something we can say small x1,
Yes.
x2, x3.
So it's 3 values.
Just three values, yes.
Yes.
And that is a homogeneous point of the 2D image point, right? So if you want to calculate the U value of the image point, you use x1 divided by x3. When you want to calculate the V value, that is x2 divided by x3. Is that clear?
Yes, very clear. Thank you so much, sir.
Is that clear, Wen?
Yeah, thank you. It's very clear.
Okay, no worries, no worries. All right, so any other questions? I mean, if there's no questions, you don't have to wait here because I'm recording, and I will upload the records to Canvas. Then you can see what the others asking and what's my answer.
Hey again, Liang. I just
Yep.
had a question about doing the transformation from the world coordinate frame to the camera one.
Yep.
I haven't really done the last lecture, so I'm kind of just getting into it. But I'm just trying to understand. I'll share my screen here. I just tried to have a go.
Oh yeah, sure. Yeah, MC, how can I stop sharing it? Yeah, there we go. Yeah.
Okay. Yeah, so it was this one here.
Yep.
This was the question. And this is how I tried to break it down.
Mhm.
So you've got the world coordinate frame here, and then you're given the translation of the camera pose relative to the world, and that's this coordinate system here.
Yep.
And then you put your point over here.
Yep.
The point from the camera coordinate system I worked out is this 15, 30, 78. And then I plugged this straight into the central projection model to find U and V.
Yep.
As you can see here, but I was off by negative S, negative the focal length for each U and V. So
Yeah,
I got, it's like, so for you, I got
probably
76, but the real answer was like 76 plus the focal length, 476. I'm not sure why exactly.
Yeah, I mean, if the UV values are minus or like larger than the resolution, so probably the projection maybe wrong, right? Because the camera cannot see it. But anyway, my suggestion is probably you
what do you mean by that?
All right, sure. So let's say if you project a point onto an image.
Yeah.
Right. And we calculate the UV values. Let's say the UV values.
Mm-hmm.
Then if the UV values are minus, what does that mean? A negative. Right. So what does it mean?
Well, it could still be on the image. Like if the image coordinate is in the middle at the principal point, then it just means it's
no
like,
UV values means the origin is on the top left.
Oh, does it? It explicitly means it's on the top left.
Yeah. So UV values means the is the origin is top left.
I gotcha. Okay.
Right.
That's the problem.
So UV values cannot be negative because they are not on the image, right? The image, the top left is 0, 0, 0. So if this is 0, 0. So if it's negative, it means it's out of the image, right? And the other way around. So let's see if the resolution of the image is 640 by 480, and you get a point which on the 700 or something, then which means it's out of the bottom right, right? So which means it's on the image. So the projection must be within the as positive and also within the resolution. So that
Okay.
means it's on. Yeah. So back to this question. You can do it in this way, but I may suggest if you can use the equation I like explained before. That makes things
Yeah,
very
I didn't really
easier.
understand. Which one was that? It
If
was-
you go back to just page 24, just page 24.
24, this one?
Yeah, that's the one. That's the equation on the bottom left.
Equation on the bottom left. Yeah, oh,
Bottom
yeah.
left. Yeah, sure, that's it. So the K is a 3x3 calibration matrix. It is
Yep,
in
yep.
Yeah, so it's in 26. It's in page 26. It's very clear there. Yeah, and yeah, so you see that, right? So this K, yeah, and
Yeah,
go back here.
homogeneous
So
matrix.
yeah, sure. And our rotation metrics are, I think you know that, right? So normally,
Yeah.
if I get identity, that's identity metrics, right? And
Yeah,
the
yeah.
3x4 metrics in the middle, which is I minus C. So I wrote it before. So if I wrote it in the whiteboard, and probably
Okay.
you can have a look in the video record later. And the X, the big X, the capital X, that is X, Y, Z, and 1.
That's fine. That's one. Okay.
Yeah, I also wrote it. I also wrote it in the whiteboard. And what you
Okay.
get is the small x on the left, right? On the left hand side, and that is 3x1. And how to convert it into UV? Then I wrote it in the whiteboard already. So in the first element divided by last one, the second element divided by last one, then you get UV.
Okay, yeah, you're just converting it back to Euclidean.
Yeah, sure.
Gotcha.
So I may suggest you just use that. And I think I have example code on that, but without R and T. But I mean, you can definitely modify on it. And this is a general projection model. I always use it
Okay.
everywhere in my research. So probably like if you have this kind of question, just use that. It's easier.
Okay. And what's
Yeah,
C again? Is C is just
C,
the
okay.
translation, the X, Y,
C is
Z
a translation. C is the translation, yeah, of the camera pose. But do remember, it's minus C, not C.
minus C. Okay,
Minus
so it's okay. So it's the world relative to the camera pose, and not the camera pose relative to the world.
Yeah.
Okay. All right. Okay, that makes sense.
Yeah, cool.
Cool. And so UV is always on the top left.
Yes, UV is always I mean orange is always top left. So when I'm saying it's a UV value of the image point, which means the orange is top left already. Yeah.
Okay. And would we follow that convention like super strictly in all topics of this this subject, like in the first few weeks with the camera and RGBD topics? Like if we got a question on those topics and U and V were like referenced variables in the question, we would always assume we would always assume the UV is specified as the top left. This isn't only specific to this week's topic.
Yeah, I think normally that's standard. So if someone telling you the image points or image locations, which means but when you probably can double check if you don't see a minus like value on the UVs, so which means it's top left, definitely. But normally we use that in that way. So that's probably that's most likely standard. Yeah.
Okay. Okay. Yeah, that's good. That's good with me then. And sorry, just to double check, is U pointing like vertically down and V is to the right?
So V is down, U is pointing to the right.
Okay.
So let's say if you have a normal like picture, so which is like the size is like a vertical, I mean, is larger than, sorry, horizontal is larger than vertical, right? So which means
Yeah.
for the U values, it can be 640 and V values is 480, something like this.
Yeah.
So V
Yeah,
is
yeah.
down and
Yeah.
U is pointing on the right.
Okay. Is that because on a camera lens, the image is like flipped and like do you know what I mean? Like when the image goes through the camera lens and then it goes onto the sensor, it's like it's flipped upside down.
Yeah, I think
And
you are right. So
maybe.
it's
Okay.
kind of like this. It's kind of like the definition of the image coordinate frame and also the camera coordinate frame. So let's say
Yeah.
you are the camera center. What your eye is camera, and you are looking up, and in front of you is the image plane, right? And
Yeah.
in the image, normally we use the horizontal one as with X and one as Y, right?
Yeah.
And in this case, that is U and this is V. And in the camera coordinate frame, because we are pointing out as Z, and we need to make it a right-hand side coordinate system. So that's why in the camera coordinate system is right is X, down is Y, not up, and forwarding is Z, something like this.
Okay. All right.
Yeah, so
cool.
let's just make it like right-hand side like coordinate system. Yeah, that's a good question. I like it. I started doing this visual slime research and like geometry things and try to understand it.
Yeah, me too. I think I downloaded one of maybe it was a recommended textbook, and it was like a whole can of worms. There are like hundreds of different models, and some of them are so much more intricate and advanced than the pinhole, and it was kind of hard to grasp.
Yeah, that's the multiple view geometry computer vision one, right? So that's a super good. Good.
Really interesting.
Yeah, probably like if you like this kind of topic, have a read on it. That's pretty good. Yeah.
Okay. All right. Awesome. Thanks.
No worries.
Yeah, I had
Sorry,
another
sir.
question. Oh, no, it's all right. You can go first.
You can go first. I can go after. I want to ask more. Yes.
Yeah, Sachin. So probably you can go first.
Oh, yeah. Yeah, I was just gonna ask, can I just screen share real quick?
Oh, yeah.
Okay. Yep, so this is my MATLAB. Just this global frame projection code that we have here that was given, and I think it was in the week 9 stuff. This can be used as a general case as well, right? Because by default, it's in the global, it's made for a question where the point is in the global frame.
That's right.
But if you want to change it so that you can have a point in the frame of the camera, you just have to make this 0, 0, right? Because you're setting that as the origin.
That's right.
Okay.
That's right. So yeah, so you can use it applying, and the general case means it can apply for different cases, right? So if it's in a global coordinate frame case, then you need to put C as the translation and R as the rotation, right? But if it's in the case that the 3D point is in the camera coordinate frame, then in that case, you just make the rotation as rotation as identity matrix. So which means there's no rotation, and translation as 0. So which means there's no translation, and you can still apply for it. Yeah.
Okay. Okay, that's good. And also I had a question about some of the continuous system stuff. So just for the linearization and then what happens after that, I was just thinking in a real question, like, so basically this stuff, it just tells you, you create a few different systems from the different equilibrium points that you find. And then you have to judge the stability of them based off what the eigenvalues are. But in a question, like, could they say, oh, okay, now choose one of these systems and then do like a pole placement or something? Like if none of these have, none of them are stable, so you want to make them stable.
Yeah,
Like-
that's a good question. That's a good question. I probably cannot answer that details about if there's a question on that, but probably like let's suppose if you have that question and how to answer that, right? Yeah. So normally, if we have that question, let's say if it's a nonlinear discrete time system, right? And then probably if you want to control it, you have to first calculate the equivalent point, right?
Okay.
Then yeah, probably go back to the slides. I mean, we have some examples about how to calculate equivalent points, and then after that, so probably you have like 2 or 4 equivalent points, and then in that case, probably I'm asking you, so at this equivalent point, try to linearize it, because linearization is at the equivalent point. At different equivalent points, then the linearization will be different, right? Yeah. And then after that, you will have a linear system. Then I may ask you if there is a, can you like check the stability of the linearized system or something, right? Then you can apply the linear discrete time system stability criteria to do that, something like this. Or like if it's not stable, then I may probably ask you how to do the pole placement. It can be different ways. It can be just a short answer questions, which means you just write the process about doing this, right? Or there may be a long answer questions, which means there may be calculations you have to do. I can't say too much if there's that question, or like if it is a short or long answer question. Sorry about that.
No,
but yeah, so you can write it in that way. So have a look at if it's short answer question or long answer question.
Okay. Yeah, and I was just wondering about this, like just what you said then about how, because once you linearize it, then you have to look for linear stability criteria. Like what in this MATLAB example,
Yes, that's right.
when they find the eigenvalues, you have to look for when it's between 1 and -1, right?
Yes, I mean, if it is linear, if it is linear discrete time system, continuous one will be different, right? But this one, okay, I think we only introduced the nonlinear discrete time system, right? So after you linearize it, it's still discrete time system.
Okay, so now, so I can just add a note here for myself. So like now that we've made it, we've linearized it, and it's now a linear discrete system instead of a continuous discrete for this specific A matrix that we create.
Yeah, so yes. So if you, I mean, we didn't introduce a nonlinear continuous time system, right? So probably like if you have a nonlinear system, and probably that's discrete time system. But I mean, double check if it's continuous or discrete, right? So I mentioned a couple of times about the how to distinguish them. Yeah.
But if we started off with the non-linear discrete, it'll just become a linear discrete, right?
Yes, that's right. That's right.
Yeah.
That's all right. Yeah.
Okay. Yeah, and also I wasn't exactly sure about what was being done here, because they've put it twice for each iteration. Like each time this runs, this gets done twice. This number is different though. There's a 2 and a 1 here.
Yeah, I think probably it's, I'm not 100% sure. I'm not 100% sure. So do you think that is for kind of the eigenvalues of A for x1 is equal to something, x2 equal to something? So probably you choose different x1 or x2, they will be different, right? So this is probably, I mean, it's calculating for each equivalent point. So different equivalent points will have different A. I think that's the case. So probably there are 2 equivalent points, and at different equivalent points will be different linearization results, and we have different like stability. Yeah.
So there's more than one A matrix.
Wait. It's kind of like you have a nonlinear discrete time system, right?
Yeah.
And then the first thing is we need to find the equilibrium point, because a nonlinear system is so complicated. We can't control it at any point. So we want to find the equilibrium point and try to control the system there. Everything, let's say linearization, and like after linearization, you can do like check the stability, controllability, and pole placement. They are all on equilibrium point. Right?
Okay.
Yeah, and different, I mean, a same nonlinear discrete time system may have different equilibrium point. Let's say when you calculate equilibrium points, then you may have like let's say two equilibrium points. You got two equilibrium points. Then at each equilibrium point, you can do linearization, you can check the stability. Because at each equilibrium point, then when you do linearization, the result will be different from the other one.
Okay.
Yeah, so that's why at each equilibrium point, you can do the linearization and will be different from the other. And then when you check the stability, it may be different from the other as well.
All right. Yeah, because you do your equilibrium points first, right?
Yes,
what you should
definitely.
do first.
That's the
Yeah.
very first. Yes.
And then from there, you can linearize into different equilibrium points.
Yes.
With
Yes.
sets. Yeah. Okay. Okay.
Yeah.
Yeah, that makes sense.
Yeah.
Okay, and yeah, just one last thing as well. Like I noticed that I guess, yeah, depending on the equation, sometimes the question they'll find the roots for one, and then they'll just sub in the roots to find the x2 values, and then other times they'll just do the roots both times.
Yeah, so that's just something about calculating the equilibrium points. So probably you can, I mean, look at this code and also go back to some examples we have in the lecture notes, and try to see like how to calculate equilibrium points.
Okay. Is that just because like, for example, for this equation they have this x1k to the power of 2 and then x1k, and then they have like the same thing with x2. So because they have two like quadratic equations, they can do the roots for both. But then for this one, where they have x1k to the power of 3 and then x1k, and then this one is x1k and then x2k, so that they can only do the roots for the first one because has the same pronumeral, and then for this one they just have to sub them in. Is that why they do that?
Okay, yes, I think that's the way why they do that. So if you, I mean, just look at the two equations on line 6 and 7, right? So the way to calculate the equilibrium point means the definition of equilibrium point means if the system at that point and the state will not change, right? So which means suppose you have two elements in the state, x1 and x2. So which means x1k plus 1 minus x1k is equal to 0. And x2k plus 1 minus x2k is equal to 0, which telling you that the state in the next stage will be the same as the state of the current stage, right? Right. That's why you have those two equations on the right. Right, but for, I mean, different questions will have different systems, so we'll have different cases. But in this question, if you can see the first equation on the line 6 on the right, so that it only contains x1, right? Then you can directly get the solution of x1.
Yeah.
Yeah, and then if you get x1, then you can probably put it into the next equation, which you can have x2, something like this.
To solve for x2, yeah. Okay, that makes sense.
Something like this. So it's a way of solving those equations, something like that.
Yeah. It's just like
Yeah, but
simultaneous
yeah,
equations.
sometimes it's not. Sometimes it's not the case. Sometimes it is. Yeah.
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 Okay. All right. Yeah. Okay. Thanks for the help.
Yeah. No worries. No worries. One. I think you have questions.
Oh yes, I have questions, sir.
Yep.
I want to know about the process of checking the stabilities of the system with non-linear discrete.
All right. So this is what I talked about. I just talked about that.
Yeah, I just want to know about the formula. So
Yeah, sure. It's hard. I mean, it's hard to explain the formulas because different questions will have different formulations, right? But I mean, the main process is first, the nonlinear discrete time system is so complicated. We can't directly control it or analyze the stability or something, right? So what we need to do is first we need to calculate equilibrium points for the nonlinear system. It can be one, it can be like more than one. All right. And then let's say I'm asking at this equilibrium point or at one of the equilibrium point, try to linearize it and analyze the stability. So this is what you need to do, right? So first calculate equilibrium points and probably choose one. And at that equilibrium point, linearize it. I mean, if you don't linearize it, you can't like check the stability, right? So linearize it, then you have a linear discrete time system at that equilibrium point, right? Then after you have a linear system, then you can check the stability.
Sorry, sir. Why should we choose only one equivalent point instead of checking all the equivalent point?
I can't answer that. It depends on the question, right? So I can say that just choose one of them, right? And then do the linearization and stability. But I may ask you like do it for all the equivalent points, right? So I can't say too much on that, but I mean, that is in the question if there is. But in the real case, let's say in the real case, if you really have a nonlinear system, you want to control it. What we always do is we calculate all the equilibrium points. We test it one by one, and to see which one is better. That's in the real case. That's in the real case. Yeah.
I mean, can I take in all the equivalent points and compare together on the test?
You mean in the final exam?
Yes, sir.
I can't say too much. I can't say too much, but probably I'm not asking you to compare between the linearized system at different equivalent points. I'm not asking you to compare them.
No, I mean according to like option. So if we choose one option, but it doesn't right, so we don't have mark. If we choose all the options and one of them right, so we have mark.
Yeah, I mean, I will write it very clearly if there is a question, right? Yes, so I may say that just choose one of them, that's fine. Or I may say like do the linearization at all the equivalent points. I will, if there is a question, I will write it very clearly.
Thank you, sir. I mean, if I do something redundant, like you told me only choose one equivalent point, but I choose all, so I have full mark for that. When I compare,
if your calculation is correct, you'll get full mark.
Yeah. Thank you so much.
No worries.
And I want to know about the eigenvalue. So eigenvalues of a nonlinear is like from between -1 and 1. So it means like the absolute value is less than 1. Like, so is it general case for only nonlinear discrete function for eigenvalue?
All right, sure. So let's say the certain criteria for discrete time system and continuous time systems are there, right? So the linear continuous time systems, then it has to be negative, right? And for all the eigenvalues needs to be negative. And for the linear discrete time system, it needs to be between -1 and 1, right? So the criteria are very clear. And then go back to your question. So if it is a nonlinear discrete, after you linearize it, what's that system? What's that linearized system?
Oh, yes.
It is still a discrete time system, right?
Yes.
So if the nonlinear system is discrete, and after you do the linearization, then the linear system is still discrete. So after linearization, it is a linear discrete time system. Then you need to use the criteria for the linear discrete time system, which means -1 and 1.
So you mean like after I linearization, it's become I transform the nonlinear system to linear system. So I just use the criteria from the linear system.
Again, the linear system have two cans.
Yes,
one
sir.
is continuous, one is discrete. The point is, if the nonlinear system is discrete, and after you linearize it, it is still a discrete time system, and you need to use the linear discrete time system criteria. That's the point.
So you mean after linearize, we have the continuous, no, we have the discrete linear system. So we use the criteria from discrete linear system.
Yes, if the nonlinear system is discrete.
So it's mean like we have to solve it first and find the equivalent point first, and we linearize and we find the discrete and we solve it. We have the discrete linear system. So we choose the case that the eigenvalue should be belong to the linear discrete system.
Yes, that's right.
Yeah, thank you so much, sir.
No worries.
Just one thing about that as well.
Yeah.
If your roots are right on 1, so for a linear discrete system or continuous discrete system, if your roots were like 0 and 1, oh sorry, your eigenvalues were 0 and 1.
Yep.
Would that be unstable?
Yeah, we call it marginally stable. Marginally stable. Yeah.
So it's like on the ball.
Sorry, just confirming. So if it's the linear discrete time system, so it's supposing you have two eigenvalues of A, one is 0, one is 1, right? That's your question, right?
Yes, yeah.
Okay, so we called it marginally stable.
Okay.
Or you can say marginally stable, or you can say stable. I'm not reducing any of the mark.
Okay,
so don't worry too much. Yeah.
And the same would be true for the continuous discrete system as well.
The continuous system is different, right? Continuous system, if you need to make, if the eigenvalues are all negative.
Oh, yeah.
Then, which means that is stable. And applies. So let's say if you have two eigenvalues, one is -10 and the other is 0, then which means it's still marginally stable.
Okay, so for continuous, they have to be negative.
Negative, yeah. So the criteria are so different. So that's why I mentioned many times. So they are two different criteria for different systems. And you need to first identify which system is it.
Yeah. Okay.
Yeah, I mentioned it many times in the previous semesters, but still get wrong answers in the quizzes and final exam. So do remember, the first thing is to double check if the system is discrete or linear. Discrete or continuous, and then use the correct criteria.
Oh, sure. Can I ask one question?
Yeah, sure.
The eigenvalues for the continuous linear system, if you're not smaller than zeros, like it's equal 0, so it's outside the range of the eigenvalue range for the continuous linear system. So how can we say like marginally stable?
Sorry, I think your internet is not very.
Sorry, so I mean, so the eigenvalue for the continuous.
Sorry, I think your internet is not very. Can you repeat it? Can you repeat it?
Yes, sir. So for the eigenvalue for the continuous linear system,
Yep.
we have the range is all of them is like negative, but if it exceeds one value is equal to 0, so it's marginally stable. I mean, if according to the mathematics function and mathematics case, so I think it's outside the range. So can we conclude that it's still marginally stable?
I think no. I think I need to correct make your question much more accurate. So if one is 0,
Yes.
and we need to see the other one. If the
I mean,
other one is positive, then definitely it's not stable, right?
yes,
So let's say for the A matrix, it only has 2 eigenvalues. One is -10, the
Yes.
other is 0. Then we can say it is marginally stable.
yes. So 0 is like something like it's not outside the range of positive, right?
It's not positive, so it
Yeah.
is on the boundary. So we can say it's marginally stable.
Okay, thank you, sir.
But
how about
I think both of you has a very good question. Normally, we call them marginally stable, but marginally stable, in the real case, is not a good one. So normally we will, in that case, we'll still like use feedback control to make it like stable. It's like normally stable, yeah, something like that. We don't want to see marginally stable. But anyway, so if there's a question, which one of the eigenvalues is on the boundary, but the other elements, so the other eigenvalues, they are like within the criteria, then you can say it's stable or marginally stable. So that's fine. Yeah.
So how about 0.0001, like 10 minus 6?
Sorry, can you say it again?
Its eigenvalue is like 10 minus 6.
It's
So
positive, right? It's positive larger than 0, right? So that is not stable. That's not stable. So that's why I'm saying even we call it stable or marginally stable, it is not a good case in the real. So in the real case, if we have that, we may consider it as we may consider to use pole placement or optimal control to make it more stable. That's in the real case. Yeah.
So
okay. Other questions?
I just have wondering about RGBD cameras. I mean the coordinates and the formula.
Yeah, sure. Go ahead.
Yeah, I mean, can I share the screen?
Yeah, sure.
One second, so I share my screen now. Yes.
Yep, I can see it.
I still don't understand this gradients magnitude.
All right. Yeah. So it is, we call it a gradient. They call it a gradient, but normally like we will not ask you to real calculate it, because I mean in the image processing, I mean there are lots of functions which can do it. But I mean I'm just explaining to you how to calculate it, right? So it's rho f rho x. The f means that the function of the image, but I mean it's in the real case it is the intensity, right? X is the x direction, which means the u direction, and y is the y direction, which means the v direction. So x is pointing to right and y is pointing down in the image, right? Okay, so then the question. Yes.
So as I know, its gradient is the direction of the derivative. So if something else like different direction, so should be minus, right?
Yeah. So this is something I want to explain. So the gradient can be positive or negative.
Yes.
All right. So
the
gradient, yes, the definition of gradient is the partial derivative of the intensity with respect to the x direction or y direction. All right. Then that's in mathematics. It's a very good question. Let me explain it to you like in very details. And then, yeah, no worries. And then in this case, because image is discrete, it's not continuous, right? Image, we have pixels, right? So instead of like a continuous function. So in the real case, what we did is we try to do an approximation to calculate the gradient. Let's say, so that I want to calculate the gradient on the x direction of a pixel, rho f divided by rho x, right? So in that case, I will use, normally I will use, let's say the current pixel is here. I will use the pixel on his right, the intensity of the pixel on his right, minus the current intensity of the pixel, right? And
I don't still
divided by
the minus. I don't understand the minus.
Sorry?
Yeah, so I don't understand the minus one you explained me.
Yeah, I'm explaining to you. Don't worry. So that's the minus is about the intensity, right? The intensity, yes. Right? So if the intensity of the pixel on the right is larger than the current intensity, the intensity of the current pixel, so which means you have a positive gradient on that point, right? But the other way around, so if the intensity of the pixel on the right is smaller than the current the intensity of the current pixel, then the gradient is minus. So it is presenting how the intensity changed on the x direction or the y direction. So it can be positive, it can be negative, right? So if on the right direction, the intensity is getting like larger and larger. For example, it's the case on the first picture on the left. Then you're getting a positive one, a positive gradient. But the other way around, let's say if from left to right, the image is getting like darker and darker, so which means the intensity getting smaller and smaller, then which means you have a negative gradient. Is that clear?
Yes, sir.
Okay, cool. That's a very good question. Well, I didn't mention it too much behind. Too much mathematics behind it. But I want to make it not so boring, so I didn't mention too much in mathematics. But it's a good question. I'm explaining to you about the mathematics behind.
Yeah, I like mathematics, so thank you so much. I just want to wonder about the gradients because it's already orientation, so it should be minus or negative or positive.
Yeah, sure. It's a good question. There are a lot of image processing method based on the gradient, because gradient is telling you how the intensity changed, and it includes some information in it.
Yes, sir. Can I ask, this formula is absolute, right? It's norm.
Right? Absolutely, yes, it's norm. Yes, that's right. Yeah, we call the magnitude. That's norm. Yes, that's right.
It should be positive.
Definitely positive. Yes, magnitude is definitely positive. It's a positive number. Yes.
Is it also like the imaginary number? So we have negative also in this.
No. It's positive. So it's kind of like a distance. Distance between 2 points, it must be like positive, right? But it's a good question. So where is the information of positive and negative of the gradient that it comes to the direction, the gradient direction, right? So if you have a gradient on the x direction with a bit larger, and the gradient on the y direction, which is a bit shorter and with a positive negative, then the theta, the angle, will be different. That includes the direction of the gradient. So the equation in the last two last two rows, it presents another way of the it's another way of presenting the gradient, right? It's converting the gradient of a point into a direction and also a magnitude.
Thank you so much. So
No
when it comes to magnitude, it should be all positive, right, sir?
All positive. You're right. Yeah.
Thank you, sir. Yeah, the Harris rotating corner, I just don't know this formula.
Yeah. So, don't worry too much. Don't worry too much. I will not ask you to calculate it yourself. But I mean, Harris corner is a very old one. It works quite well. So when I did my first year of my PhD, I used that because I did photogrammetries. I mean, 3D reconstructions from the images taken from the UAVs, from the airplanes. And if you look at the roof of the buildings, then there are lots of physical corners, and that's why Harris corner is popular there. And yeah, so for Harris corner is mainly extracting the physical corners, and it's also using the gradients as the equation, something like that. So if you are very interested in it, so probably search the Harris corner detection. And there's a paper explaining that, and it's a very interesting one. Probably you can have a look. Yeah.
Thank you so much, sir. But is it really hard questions for this in the exam? I just was wondering.
Yeah, it's kind of like is trying to calculate a pixel, and also its gradient on different directions. And the second order moment matrix is mainly telling that if the current pixel has like gradient on two different directions. Let's say if you have a corner, right? If there's a corner, that means on the two different directions it has different gradient, right? Let's say if there's a line. If it's a line and there's a pixel on it, so on one direction, there's a gradient, large gradient, right? But along the line, the gradient will be 0, right? So that's a line. But for the corner, it will be different, right? So for both two directions, they will have large gradient. So which means reporting it is probably a corner. So that is the main purpose we have this second moment metrics.
Thank you, sir. So it's
No
only
worries.
the sum of this.
Yes. Yeah.
Thank you so much, sir.
Hey Liang. I just had
okay.
another question, just a quick one. I'll
Yep.
just share my screen quickly, if that's all right.
Oh yes,
Yeah.
yes.
Sure.
Okay. So linear discrete time system. I saw in a previous exam paper, it was asked to calculate the solution of the state of x of k. So just like here, I just wondered, would this response here be sufficient?
I can't see the screen now. Sorry.
Oh, sorry. Thought I was. Okay. Can you see now?
Here we go. Yeah. Sure.
Okay. Cool.
Yeah, that's enough. That's enough. So
that would be sufficient.
I don't require you to like to calculate
Like resolve it. Yeah.
the power over matrix inside. Don't have to. You just write the standard equation and replace the A and B with actual ones, and that's it. Yeah, that's the one I want. Yes, you are right.
Okay. No worries. Okay. Awesome. Thanks a lot.
No worries. One. So you still have questions?
Oh yes. I just look over the tutorials, but also finding some questions outside. Is it alright, sir, or just only tutorial?
Probably not talking about tutorials. Yeah, so it's mainly about let's just talk about the questions, sorry, the lectures itself. Yeah, because I mean, it's It's a final exam. I'm not requiring any of the computer experiments.
Thank you, sir.
No worries. All right, so when you don't have to wait here. So I'm recording everything and I can share it, upload it into Canvas.
Thank you so much. Can I ask you just one more question? And
Yep.
so I'm going around the assignment on the tutorial, but I'm also finding outside. Is it? Is it really hard questions on some cases, like really non-linear discrete or Harris?
I can't say that. I'm sorry, I can't say that. It's only 2 questions. If I'm saying very detailed, you know what is it? Sorry about that. Yeah.
Thank you so much for your answer. Yes.
No worries, no worries. So don't worry, you don't have to wait here. I'm recording everything. So if someone asking things, and I will have another consultation time on Monday. So if you have some other questions following, then you can come to that session as well. All right.
Thank you so much. Have a nice day, sir.
All right, you too. See you.